This is 30-minute session. We're going to have 3 speaker slots, but the last slot is going to be 2 speakers. Without further ado, I'd just like to start right away. Let me just bring up the schedule. And then our first talk is by Gong Zhang. Let me just check. Do we have, sorry, I'm lost in the windows here. Oh, there it is. Okay. Our first speaker is Gong Zhang. I'm sorry, I just trying to bring the window back and somehow I have lost it. Yeah, the hazards of online conference like this. Okay, got it. Okay, great. So Gong, please go ahead.
Okay, hello everyone. Thank you for joining my talk. My name is Zhang Gong from National University of Singapore. Today, I'm glad to be here to introduce you one of our recent work entitled Securing Practical Quantum Cryptography with Optical Power Limiters. So let me start the story by showing you a lot of practical attacks into a QKD system. And simply speaking, we can characterize them based on the target, either receiver or the source. But for the transmitter, luckily we have the MDI-QKD, which could close the detector loopholes. But for the transmitter side, we still have to find a practical and secure way out. And power limiter or energy bound is one of the important tools. And one main application is to solve the Trojan horse attack problem. So for Trojan horse attack, in a QKD system, if could inject a strong light into Alice equipment and collect the reflective photon with the encoded information, it is dangerous and couldn't be detected by just looking at the error rate. So there are a few previous works to counter such attacks, and the basic idea is to limit the amount of unauthorized input power. And another field requires energy bound is the semi-MDI-QKD or QRNG. And as long as we can trust the energy bound, the QKD or QRNG will be secure. And again, a power limiting device is very important here. There were a lot of previous work that could provide energy bound in an optical system. One could depend on the fiber damage or just use a filter. And another type would be based on the nonlinear effect, like two-photon absorption or Thermo-Optical defocusing. And here our power limiter is mainly based on density effect because of the relatively low threshold and the simple design. This page I show our power limiter design. We have input-output fiber as the interface, and we have a pair of collimators to collimate the light, and an active medium with negative thermo-optical coefficient is put in the optical path. And here we choose acrylic. And the input laser will heat up the center of this material, which could reduce the refractive index here and make the prism look somehow like a concave lens. And then if we put a diaphragm here, we can control the received power. And a filter here could be introduced to prevent wavelength attack. And we provide more detail on the full length video online. So basically that's it. All we use is the off-shelf components to provide robust and cost-effective design. And in this page, I show we show the power limiting function could by both the simulation and experiment. In this figure, you could see at first, the output power will just increase with the input. And after a certain threshold, the output will start to decrease. And by changing the prism length or the diaphragm width, we can either shift the curve or change the shape of the curve. And also we consider other degree of freedoms, and I won't go into the detail due to the time limitation. So basically here we prove that the power limiter is also working for pulse laser. And this page we show that we notice the wavelength dependency of such power limiter only comes from the material absorption spectrum. So that is why a visible filter could also help. And for laser damage attack, we provide a solution by using the reflective structure like this. And finally, I will introduce you one of the main applications of such a power limiter, plug-and-play MDI-QKD. The system will look something like this. The advantage of plug-and-play MDI is that the user doesn't have to purchase expensive laser and detectors. And with a common laser source here, the wavelengths could be identical for both Alice and Bob, and the clock synchronization will be much, much easier. But the main issue prevent the application for being used is the Trojan horse attack. And that is why we need to put a power limiter here. And we did a simulation here shows that even if we consider some average Trojan horse photon leakage, we are still able to bound the information without much compromise on the total performance of the system. Yeah, so as a conclusion, I would say this is, to the best of our knowledge, quite complete analysis of such a cost-effective passive power limiter. And still, we are open for advices from you and collaboration on this work. And I would like to thank Professor Charles Lin and Professor Gong Xiao and all my colleagues for their contribution and support on this work. And thank you all for the listening.
Yes, unmute. I was muted. Thank you very much. So thank you very much, Gong, for your talk. So let's move on to the next one by Tobias Gering, who's going to tell us QKD and machine learning. So another talk with mixing machine learning and QKD or QRNG. So
thank you very much. Yeah, I'm happy to present our work here at QCrypt about a continuous variable QKD implementation using machine learning. So let's directly jump into it. This is a schematic of our QKD system. We have a transmitter on the left, a receiver on the right, and quantum channel in the middle. We use a continuous wave laser in the transmitter station and an in-phase enquadrature modulator to generate coherent states with a Gaussian modulation. On the receiver side, we implement a heterodyne detection, so we measure amplitude and phase quadrature at the same time using a technique called radio frequency heterodyne detection. So we just use a simple single 50-50 beam splitter and then a local oscillator laser that is frequency detuned to the transmitter laser. And in that way, we can actually measure both quadratures at the same time. Our laser at the receiver is free running to the with respect to the transmitter laser, and therefore phase compensation is very important. So if you don't do any phase compensation, then the correlations between the symbol we measure and the symbol that was modulated is very bad, and that is roughly what you can see on the left. So we actually have to perform phase compensation, and we do this by also modulating a so-called pilot tone onto the light. So the pilot tone is a sine wave that is frequency multiplexed to the quantum signal. And what you see here is a typical receiver spectrum. So you can see here on the right, this is the beat between the two lasers. It's about 200 megahertz. The x-axis is missing here. So this is the frequency detuning. Then we have the quantum signal sitting here and a pilot tone that we then measure, and we estimate the phase of this pilot tone to actually compensate the phase of the quantum signal. The trick is now to do this phase estimation in an optimal way, and our method uses a Bayesian inference approach based on an unscented Kalman filter. So Bayesian inference is a well-known technique for parameter estimation from statistics. And what you need for this is, for example, the prior information. Prior information here is about the laser noise, the laser phase noise. And this is a problem because, well, a perfect laser follows a Wiener process, but nobody has a perfect laser. So we actually do not really know how this this phase noise model looks like. And this is what we are learning from the data, so that we do not need to know it in advance. The second problem is that usually Kalman filters work for linear systems, but our system is actually non-linear because this is the pilot tone, well, it's a sine wave, and this is the phase here we want to extract. So there's a sine relation between, and we have to deal with this non-linear system. And this is what the Kalman filter does. And it does it by approximating the posterior probability distribution by a Gaussian. So the posterior probability distribution is what the Bayesian inference approach is estimating. So we estimate that by a Gaussian. And then we propagate actually the mean value and plus minus the standard deviation directly through the nonlinear system. So we do not linearize that system. And these are our results. So here on the left, you can see the pilot tone signal to noise ratio. This is basically how much power we have in the system, how much we filter the system. And on the x-axis, you can see the excess photon number. This is basically the figure of merit for a QKD system. And what you can see here in blue is the excess noise we achieve by using our phase compensation algorithm, which is very broad for the signal to noise ratio, so it doesn't really matter what to choose. And we compare that to mainly the reference method, which is basically just taking the Arcus tangents between the amplitude and phase quadrature values. And for very high signal to noise ratios, they converge, they work equally well. But in our case, we can actually use much lower power in the pilot signal than is otherwise possible. This translates into a secret key rate. It's just basically 1-to-1. And with this, I would like to summarize. So we can show that using our technique, we have good performance over a large range of signal to noise ratios. That means we are very robust against environmental changes. And it works also in the low signal to noise ratio regime, which has implementation advantages because we can really use very low signal pilot tone powers. Thank you very much.
Great, thank you very much, Tobias. So before going to the next talk, I remind you that you can ask questions anytime in using the Q&A feature of the Zoom, so please go ahead. And then with this, we're going to move on to the next talk, which is two talks merged into one by Wei Luo and Kai Lin. So please go ahead.
Okay, thanks, Chair. Hello, this is Wei Luo from Technological University. And today, my colleague Salin and I would like to give a brief introduction on our work on chip-based QKD system. And first, in the first part, I will present our recent progress on the integrated chip platform for measurement in device-independent QKD. As we can see in the recent years, more and more researchers have been involved in the studies of embedding quantum photonic applications into scalable integrated devices. And the technology of integrated quantum photonics has enabled the generation, processing, and detection of quantum state of light in a small chip at a steadily increasing scale and level of complexity. Until now, a range of optical waveguide platforms have been developed for the integrated quantum photonic applications. Among these platforms, in our opinion, we believe that silicon photonics is an optimal choice for QKD because it can provide the most mature solution compatible with CMOS fabrication process and promise fully integrated QKD with integration of detectors and lasers. And typical on-chip QKD demonstrations can be seen in the work from researchers of University of Toronto in 2016 and University of Bristol in 2016 and 2017. In their work, they implemented various CV QKD protocols using their chip scale transmitters and receivers. Our group has also demonstrated that silicon photonic chip platform for CV QKD in 2019. And for the further development of QKD systems, chip-based QKD systems, we are looking at the integration of MDI-QKD. We know MDI-QKD removes the detection loopholes, and its architecture is naturally suited for multi-user QKD networks. Since the most expensive and intricate component, the measurement device, can be placed in an untrusted relay and shared among many QKD users. That means each QKD user only needs to hold the transmitter, and the integration of the transmitter will greatly reduce the cost and improve the flexibility of the QKD network. Of course, the integration of MDI-QKD server is also possible. And based on these ideas, we have developed a chip-based MDI-QKD system by integrating both transmitter and the server chips. Here we show the fabricated silicon photonic transmitter chip and the server chip. And using these chips, we perform a proof of demonstration to demonstrate our feasibility of our chip scale MDI-QKD system. In the demonstration, we implemented 4-intensity decoy states MDI-QKD protocol proposed by our collaborator, Professor Xiangping Wang. And the QCrypt per pulse of our system is about 2.9 times 10 to the minus 6 over a distance corresponding to 50 kilometer optical fiber link. And this result agrees well with the simulation. And we can see it is also comparable to other MDI-QKD studies, including 2 recent chip-based MDI-QKD systems. In conclusion, we have developed an integrated photonic chip platform for MDI-QKD and perform a proof of principle experiment to demonstrate the feasibility of the system. And both the transmitter and server chips for MDI-QKD have been fabricated using silicon photonic technology. And in the future, with further integration of laser diode, optical switch, and single photon detectors, and it's possible to build a fully chip-based MDI-QKD platform with high scalability and low cost. And that's all for the first part. In the next part, our colleague Cao Lin will present his work.
Hello, everyone. This is Cao Lin from Peking University and Nanyang Technological University. My talk is about on-chip time and polarization-multiplexed continuous variable quantum key distribution. By now, many experimental demonstration has been showing the feasibility of CV QKD with coherent states. And last year, an integrated silicon photonic chip of CV QKD based on continuous wave has been demonstrated. However, a much more practical CVQK chip-based CVQKD system based on pulsed operation and time and polarization multiplexing has not been demonstrated till now. So this work is include the fabrication and the design of CVQKD chip, which includes the transmitter chip and the receiver chip. This chip is used time and polarization multiplexing, which enable signal and local oscillator light to share one channel and reduce crosstalk between them. And all the components are integrated on the chip. This figure shows the layout of our CV QKD system. The box above shows the transmitter chip, and the box below shows the design of receiver chip. On transmitter chip, we use the 3 identical amplifier modulator to generate a loud pulse with high pulse acting ratio. Here, I only show the testing result of 1 modulator. This figure shows the static pulse acting ratio. The acting ratio is up to 35 dB, and the dynamic pulse acting ratio at 5 MHz is larger than 21 dB. This figure clearly shows identical and stable light pulses can be generated in a long time. In our previous work, single polarization beamless splitter only provide about 25 dB polarization isolation. In this work, to reduce the crosstalk between signal and the local oscillator, we designed a new PBS. The testing result shows the polarization exchange ratio of the new structure can provide about 30 dB polarization isolation, which meet the requirements of CV QKD system. The system noises are carefully measured. This figure clearly shows the electronic noise is about minus 83 dBm, and the noise to the signal to noise ratio is about 8 dB. With the modulation on, the measured output is at about 12.5 higher than the short noise. So the modulation variance is about 12.5 short noise units. Now, the parameters we have measured are summarized in this table. Based on the parameters, the simulation of secret key rates under different conditions are performed. These three figures respectively shows the influence of excess noise, detector efficiency, and the reconciliation efficiency on secret key rate. This result shows our CV QKD system is expected to perform well and generate a positive key rate under larger excess noise or low reconciliation efficiency. To sum up, we designed and fabricated an on-chip time and polarization multiplexed continuous variable quantum key distribution system, and key components of chip and the system noise are carefully measured. Finally, the simulation of the secret key rate under different conditions are calculated. In the future, we will continue to demonstrate a long-distance CV QKD using this chip-based system and generate a real key rate. That's all. Thank you for your listening.
Great. So thank you very much to all the speakers of the session. I will let Hugo continue with handling the questions.
Yes, so we have a few questions. The first is by Vadim Makarov. So Vadim, you can unmute and then you can talk.
Thank you. I have the question about the first talk about the power limiter. Do you hear me well?
Yes.
So in your MDI-QKD model, do you have to input relatively high power at Alice and Bob such that their limiters stay in a saturated regime at all times?
No, for this question, no, because we just like provide an energy bound, upper bound for if how much Trojan horse photon Eve can get. So they don't really need to always saturate the polygon limiter. So it's just like a protection of fields. So everybody just working at the safe zone. But if there's Trojan horse attack coming from Eve, then the security is bounded by the power limiter, just like that.
But what would then stop Eve from just increasing the input brightness and getting a higher output brightness from Alice and Bob?
I think that's just from the output input curve we provided. It's like if you provide a higher input power, then the output will just start to drop, and it will provide us like a upper bound for the output power. And yeah, it's just like to something like that. As I don't know if I understand your question correctly.
Okay, I'm not convinced the scheme will actually protect against Eve that will use pulsed input signals at Alice and Bob, but we can discuss this in the break.
Okay, yeah. Also, I saw your second question regarding the pulse. Are you referring to that? Yeah. So if using a pulse laser, as we explained in the presentation, the security of such a power limiter is calculated by an average Trojan horse photon over like a slightly longer period. So one assumption we have is we need to operate the QKD device for a longer period, longer than the response time of such a power limiter, so that the average output power can be characterized correctly.
Okay. So maybe we go to the next question. It is by Adamas Baliuka. So Adamas, you can go ahead, please.
Hello, my question is for Tobias Gehring. From a security perspective, are there no dangers in using a trained machine learning system whose response to all possible inputs can usually not be fully qualified in a QKD protocol?
Yes, so thank you for this question. So in general, I would say that I don't see a difference between the Kalman filter-based approach we have and the reference method for extracting the phase. But in general, your question is good because the question is, can I really use a pilot tone or a reference pulse, or does that open a security loophole? I think this is still an open question that is debated. My take on this is there's no loophole as long as the additional phase noise I get because of this imperfect phase estimation is not trusted. As soon as I trust it, I open a loophole. But as long as I don't think there is a loophole by using pilot tones or reference pulses. Hope that answers your question.
Okay, then maybe let's move. Is this okay for you, Adamas?
Yes, thank you.
Okay, excellent. So then you have another question from Rupesh. I think it's also for Tobias. Rupesh,
hey, Tobias, hi. I have a couple of questions. One is compared to the phase estimation from reference pulse, what is the advantage in terms of key rate and the transmission distance if you use this piloton?
Yes, thanks, Rupesh. So in our case, in our implementation, the pilot tone power was a mere 3 times higher than the quantum signal, and for us it made basically the difference between generating a key and not generating a key at 20 kilometers. But in general, you can of course increase the pilot tone power and always achieve same performance. So in that case, it is, I would say, an implementation advantage, because if we increase the pilot tone power, well, we need more bits in our digital to analog converter, for example. And maybe there's noise spilling from the pilot tone into the quantum signal. So maybe we have to take it further apart. Or as other groups did, maybe we had to polarization-multiplex the pilot tone to get to use high power. So it is an implementation advantage in that sense. But I think you can always achieve the same performance by just cranking up the power.
Okay. Okay, thank you for that. And my second question is, maybe I didn't understand much better about this one. So your piloton is slightly frequency offset as that of the quantum QKD signal. So in that case, the phase estimation from piloton, how exact that the phase of the quantum signal? Is there any offset? And if there is an offset, does that offset fluctuate because there are different frequencies? They are passing through the different, through the fiber, so they occur different phases. So does that phase change randomly? And in that case, how do you manage it?
Yes, so there is of course a phase offset, fixed phase offset, because your detector has maybe a different phase profile, but this is something that does not change. And I think the difference in frequency is rather low, right? It's just a couple of 10 megahertz. So we don't see any fluctuations in phase between the quantum signal and the pilot term. and not randomly.
Okay, thank you. May I, one more thing, may I ask one question to Guang Shang? It's about the power limiting QKD, securing QKD system, but he completely forgot about the CV QKD side of it. At least some of the CV QKD attacks, they don't need much power. For example, the saturation attack. So in some cases, the power testing based on the power of the incoming signal doesn't work. It's a comment.
Oh, okay, thank you.
Okay, let's go. Actually, Gong Zhang has also a question to Tobias.
Yes, I was thinking, is there any special reason for using like a 220 megahertz separation for the two lasers? Do you have to somehow lock it?
No, there's no particular reason in using 220 megahertz. Could also be less or more. You just have to make sure that all the mixing products do not overlap, so that they clearly are apart. And this is, what we ended up with. There's no particular reason on that.
Okay.
Could be 400.
Can it be lower, like we set the wavelengths to be exactly the same?
Yeah, if it's exactly the same, then it doesn't work, because then you get into the homodyne detection regime, but we call that intradyne if it's close, because then you get mixing products between the different sidebands.
Okay.
In our case, this would not work. We would then need an optical hybrid to actually measure the other quadrature as well.
Okay. Yeah, another question is that, is it possible like for Eve to attack by also locking to, because you're sending a frequency reference, is it possible for them to lock to the frequency reference to do the attack?
Yeah, that goes back to the first question about the pilot tone. If the pilot tone can be attacked, I don't think so.
Okay, thank you.
Okay, well, I think we can go on for questions. But Christian, you agree on that? We don't have to close this session immediately. So we have a next question by Chao Wang, please.
Okay, thanks. Thank Wei Luo and Cao Ling for your great talk. So I have a question for you. So the first question is for the MDI chip-based MDI-QKD, right? So I think some groups has demonstrated this kind of chip-based quantum transmitter, right? So they will observe some phase modulation related loss problem, right? So I'm wondering whether you also have this question, you also have this problem, and how you solve this problem.
Yeah, okay, thanks for the question. Actually, yeah, we have the similar problem with the modulation related loss, and it will influence the security of the system and open some loophole. So actually our solution, maybe we can solve this problem by adding an extra high-speed VOA, variable optical attenuator, to compensate the modulation related loss caused by the polarization state encoder.
I see. But this kind of high-speed VOA hasn't been included in your current setup.
Yeah, in current setup, we didn't include in
I see.
this kind of VOA, yes.
Okay.
But
okay.
Yeah. In the next design, we will consider this problem.
Yeah. Thank you very much. And my next question, my second question is for Cao Ling. So because I noticed, right, the homodyne detector you are using it has a bandwidth of around maybe 10 megahertz. Because you only show the bandwidth of the homodyne detector to 10 megahertz, right? So, and you are also doing time multiplexing on the optical chip. So I'm wondering how long is your delay line on your chip? And how about the repetition rate of your system, right? Whether the long delay line on chip will introduce quite a lot optical loss to your system, right? Will it be a problem?
Okay. The operating rate of our system, the pulse repetition is about 5 megahertz, and we encode signal by amplitude and modulator. The frequency is about 6 MHz. And we use 20 meter off-chip fiber as the delay line. And the loss is the loss of the fiber is very small, but the coupling loss of chip is about 5 dB.
Okay. Yeah. Okay. Thank you very much.
Thank you. So maybe we come to our last question. Nitin, you can ask it directly.
Hi. So my question is for Chaolin. I hope I pronounce the name correctly. So you reported polarization extinction ratios of like 30 dB or even 40 dB, and as far as I know, typical fiber optical polarization beam splitters have like 20 dB, at the most 23 or 24 dB. So how did you get such a massive improvement?
Okay, thank you. We actually on-chip single PBS can achieve the extinction ratio about 25 dB, and we use two PBS together and the two cascaded PBS, and this can achieve much higher extinction ratio.
Okay, great. That explains it. Thank you.
Thank you.
Thank you very much. I pass the word to Felix for a conclusion.
Yeah, so thank you very much again to all the speakers for this great session.